better. So minimal, it doesn't matter. The point is that we can do the same thing here for arbitrary flows, not just minimal flows. For minimal flows, it's much easier to find universal objects. So anyway, that's the motivation for this construction in the first place. But the question, well, there are two questions that I really want to leave you with. So one question is just based on an observation that there are only two models I really know about concerning this quotient relation. So I've only been studying this relation for a very, very brief time. So CH, I've done a little bit of work. And PFA, or OCA plus MI, is the other model in which it's not too terribly difficult to say a few things about this relation. And in both models, it's true that every autohomomorphism of omega star is the quotient of a trivial one. I just showed you why that's true under CH. And it's trivially true under PFA because there are no non-trivial autohomomorphisms. So the question is whether that can be proved in CFC. My hunch is no. But the reason I think this is an interesting question is because, on the one hand, the methods that we have for proving that this is true in the two models I mentioned are extremely different, right? It's true in both models, but for completely different reasons. It's true under PFA because there are so few autohomeomorphisms. It's true under CH because there are so many quotient mappings. Because we can, no matter how bad we try to build an autohomeomorphism, we can always make a quotient mapping from a trivial autohomomorphism that has enough badness to catch it in some sense. So on the one hand, it seems like this should be just a coincidence that this is true in both models. On the other hand, it seems to me that it could be fairly difficult to get a counterexample and enforce it. Because the way that I would initially think to go about it is to try to force some sort of really, really bad autohomeomorphism of omega star. But the problem with doing that is that as soon as you create new autohomeomorphisms of omega star, you're automatically creating new candidates for quotient mappings. Because quotient mappings are just continuous surjections of omega star onto itself. So you can't create continuous bijections without automatically creating lots and lots and lots of continuous surjections. And it's really not clear to me how you can make the continuous bijections bad enough to outrun all of the continuous surjections that you're simultaneously creating. So all that to say, I have no idea how to solve this problem, but I would love to see if one of you can figure it out. The other question I want to mention, it's one that I've worked on quite a bit before. So I'm phrasing it in a very specific form here. Omega star with the shift map, is it isomorphic to its inverse? Now by isomorphic, what I mean is that the quotient mapping from one to the other can be made to be bijection, a homeomorphism. So that in a sense, these two maps are doing the exact same thing up to a renaming of points. So are these the same map? Does omega star know the difference between +1 and -1? Is another way of putting the question. But this is, in some sense, an instance of a bigger question. So this, I'm just going to go back here real fast. Again, this lifting idea here, using the elementary to accomplish this lifting, actually gives us a fairly straightforward decision procedure for deciding when two trivial maps are quotients of each other under CH. What it lets us do is look at one potential quotient mapping and just and look at another. It lets us look at two trivial autohomomorphisms and in a relatively short amount of time be able to say either yes or no, one is a quotient of the other. And what I would really like to be able to do is come up with a similar technique for quickly deciding when two trivial autohomomorphisms are isomorphic. And at the moment that seems to be out of reach, but I think this is a good test question for that problem. And so that's one of the reasons why I'm posing it here. And that's all.
Are there any questions for us?
Not a question, but I think people would be interested to know the answer to your last question under PFA.
Oh, right. So under PFA, they're definitely not isomorphic. Under PFA, they're not even quotients of each other. So that they're not isomorphic is fairly easy to show because any isomorphism would have to be a trivial autohomeomorphism, and you can sort out pretty quickly that there isn't one sending sigma to its inverse. To show that they're not quotients of each other uses some of this machinery that Farah has developed concerning the structure of continuous functions from Vega star to itself. And using that machinery, you can produce an argument that shows you can't even map one of these onto the other. So they can be very far from isomorphic. I should also mention that if they are isomorphic, it should happen under CH.
And under CH, they are quotients of each other?
They are quotients of each other under CH.
And the mapping is that the quotient mapping
is produced by an argument similar to this one. So it's not transparent.
But you know that the one produced by that argument is not a...
Yes. So this argument cannot produce isomorphisms by itself. And I can show, in fact, that just because two things are quotients of each other does not make them isomorphic. So just knowing that they're quotients of each other, it's sort of hopeless to go that road and hope that this pre-order of the quotient relations somehow generates something a bit nice among its equivalence classes. It doesn't. The equivalence classes are, in other words, larger than the ones you get by isomorphs.
Any other question or comments?
I guess just a very naive question. I mean, what roadblocks do you stumble into to try to increase the length of this inverse limit chain?
Yeah, sure. That's a good question. So I'll answer that in two ways. So the first way is that I know there must be roadblocks because the argument definitely fails in the Cohen model.
Right.
So if I add LF2 Cohen reals, then the conclusions of the theorem stop being true. So something bad must happen to the argument, right? What happens that's bad is the lifting step. So when you try to use elementary submodels to find these reflections of omega star with H on it, when all of your reflections are countable, then going from reflection alpha to reflection alpha plus 1 entails gaining countably many new coordinates. And the way that the lifting step works is to sort of successively approximate the topology in the alpha plus 1 level coordinates using a countable sequence of open covers. And once you're dealing with sequences of length omega 2, the bad thing that happens is that going from step alpha to step alpha plus 1 entails gaining omega 1 new coordinates, and you can no longer do that. You can't organize, in other words, all of your new open covers into a nice countable sequence where each one is a refinement of the next. And it's that really allows the lifting to take place. So it's kind of a hopeless non-starter, to be honest. Right.
Morass.
That's a good point. I've thought about this with relation to
by now.
yeah. So I don't like morasses, but I do like, and David will appreciate this. I do like these Davies trees, right?
Yeah,
So
that's what I was going to say. Try that.
right. So I've looked at them, and they don't seem to work either. For reasons that I'm not sure I understand quite as well. But I do know that the full conclusions that you can draw from this proof technique under CH do stop being true, even when you have these nice Davies trees and things. So something goes wrong. I'm not sure whether you can, under certain further assumptions, do something with Davies trees, hopefully, or morasses, if I have to go there. Yeah, I'm not sure. But it's a great question in one word.
Any other questions? Okay, let's thank our speaker.